Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about understanding the Carnot, Otto and Brayton cycles. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Okay guys, first let's make a little revision. As we learned from previous lessons, thermodynamics is a branch of physics that studies the relationships between energy, work, and the physical properties of systems. In simpler terms, it helps us understand how energy is transferred, transformed, and conserved in different physical processes. Unlike microscopic physics, which focuses on the behavior of individual molecules or atoms, thermodynamics deals with the large-scale, measurable responses of entire systems, things we can observe and quantify in experiments. For engineers, and especially for aerodynamicists, thermodynamics plays a crucial role in understanding propulsion systems and high-speed aerodynamic flows. The propulsion system of an aircraft, for example, generates thrust by accelerating a working fluid, usually a heated gas. According to Newton's third law of motion, every action has an equal and opposite reaction. So when the propulsion system accelerates the gas in one direction, the aircraft experiences a force that pushes it in the opposite direction. To fully understand how such a propulsion system operates, we must explore the fundamental thermodynamic behavior of the working fluid itself. The working fluid and its properties. The working fluid in most propulsion systems is a gas. Gases exhibit several measurable properties such as pressure, P, temperature, T, mass, and the volume V they occupy. Through careful scientific study, we've learned that these properties are interconnected. Changing one variable, like increasing the temperature, often affects the others. Together, these properties describe what we call the state of the gas. In addition to these measurable quantities, thermodynamics introduces two more important state variables, enthalpy and entropy, S. Enthalpy is a measure of the total energy content of the system, while entropy represents the degree of disorder or randomness in the system. When a gas undergoes a thermodynamic process such as being heated, cooled, compressed, or expanded, these state variables change in specific ways. The amount of work done by or on the gas and the amount of heat transferred depend not only on the initial and final states, but also on the specific process path taken between them. Visualizing thermodynamic processes PV and TS diagrams. To better understand how these state variables change, engineers and scientists often represent thermodynamic processes on graphs. Two of the most commonly used plots are the pressure volume PV diagram and the temperature entropy TS diagram. On a PV diagram, pressure is plotted against volume. Curved lines on this diagram represent states of constant temperature, known as isothermal processes. When a process occurs at constant temperature, it follows one of these curves. Another important process, the adiabatic process, occurs when no heat is transferred into or out of the gas. During an adiabatic change, the pressure, temperature, and volume all vary, and this process typically appears as a steeper, dashed curve on the diagram. The area under the curve of any process on a PV diagram represents the work performed by the gas during that process. The TS diagram, on the other hand, plots temperature against entropy. On this type of diagram, lines of constant pressure, called isobars, usually curve upward from the lower left to the upper right. A process that occurs at constant pressure is called an isobaric process, and this kind of process takes place, for example, in the combustor section of a gas turbine engine. Another key process is the isentropic process, during which the entropy of the system remains constant. This means the process is both adiabatic and reversible. On a TS diagram, an isentropic process appears as a vertical line. Interestingly, the area under a process curve on a TS diagram corresponds to the heat transfer involved in that process. Thermodynamic cycles and their importance. A thermodynamic cycle is a sequence of processes in which a working fluid undergoes various state changes, but eventually returns to its original condition. This concept is essential in understanding how engines and other energy conversion systems operate. Each cycle consists of several stages, and throughout these stages, energy is alternately added to and extracted from the working fluid. Different types of cycles are used to describe different machines. The Carnot cycle represents an idealized process that helps us understand the theoretical limits of efficiency for heat engines and refrigerators. The Otto cycle models the operation of internal combustion engines, such as those found in cars. The Brayton cycle, meanwhile, explains how gas turbine engines function. These are the engines commonly used in aircraft propulsion. By studying these cycles and representing them on P, V and T, S diagrams, engineers can visualize how energy is transformed within a system, identify sources of inefficiency, and design engines that perform more effectively. Understanding these thermodynamic cycles is therefore a key step in mastering the science of propulsion and energy conversion. The Carnot cycle, the foundation of heat engines. In thermodynamics, it is possible to carry out a sequence of processes in which the state of a gas changes during each step, yet after completing all the steps, the gas returns to its original condition. This complete sequence of transformations is known as a cycle. Cycles are fundamental because they form the basis for understanding how engines and other energy conversion systems operate. Among all the thermodynamic cycles, the Carnot cycle holds a special place. It represents an idealized model of a heat engine operating at maximum possible efficiency. To understand how the Carnot cycle works, imagine a gas enclosed in a cylinder that is fitted with a movable piston. The gas serves as the working fluid of the cycle. The cylinder is in contact with two heat reservoirs, a hot reservoir at a higher temperature, around 300 degrees Celsius in our example, and a cold reservoir at a lower temperature, about 200 degrees Celsius. The piston's position determines the volume of the gas, while the weights placed on it determine the pressure inside the cylinder. Initially, the gas is at a high temperature, high pressure, and low volume. This is referred to as state 1 on the pressure, volume, PV diagram. Step 1. Isothermal expansion from state 1 to state 2. The first process in the Carnot cycle is isothermal expansion. During this stage, the gas is brought into contact with the high temperature reservoir at 300 degrees Celsius. Some of the weight on the piston is removed, which reduces the pressure on the gas and allows it to expand. Because the gas is in thermal contact with the hot reservoir, its temperature remains constant throughout the expansion. However, as the gas expands and does work on the piston, it requires a continuous supply of heat to maintain this constant temperature. This heat, denoted as Q1, flows from the hot reservoir into the gas. By the end of this process, the gas has expanded to a larger volume and a lower pressure, reaching state 2. Step 2. Adiabatic expansion from state 2 to state 3. Next comes the adiabatic expansion. In this process, the gas is thermally isolated from both heat reservoirs, meaning no heat is exchanged with the surroundings. Additional weight is removed from the piston, allowing the gas to continue expanding. As the gas does work to push the piston outward, its internal energy decreases. Since no heat enters the gas to compensate for this loss, its temperature drops naturally. By the end of this stage, the gas reaches state 3, characterized by a lower temperature, lower pressure, and higher volume than before. Importantly, the heat transfer during this process is zero. Step 3. Isothermal compression from state 3 to state 4. The third step is isothermal compression. Now the cylinder is placed in contact with the cold reservoir at 200 degrees Celsius. We begin adding weight back onto the piston, which increases the pressure on the gas and compresses it. Because the gas is in contact with the cooler reservoir, its temperature remains constant during this process. However, as the gas is compressed, it releases heat to the surroundings. This heat, denoted as Q2, flows from the gas into the cold reservoir to maintain the constant temperature. By the end of this stage, the gas has returned to a smaller volume and higher pressure, reaching state 4. Step 4. Adiabatic compression from state 4 to state 1. The final stage of the Carnot cycle is adiabatic compression. During this step, the gas is again thermally insulated from both reservoirs. More weight is added to the piston, causing it to compress the gas further. Since no heat can escape or enter the system, the work done on the gas increases its internal energy, which in turn raises its temperature. By the end of this process, the gas returns to its original high pressure, high temperature, and low volume condition back to state 1, where the cycle began. Work done and energy conversion. At the end of the Carnot cycle, the gas has completed a full loop of processes, returning to its starting state. This means the internal energy of the gas is the same as it was at the beginning. However, during the cycle, energy has been exchanged in the form of heat and work. The gas has absorbed heat Q1 from the hot reservoir and released heat 2 to the cold reservoir. The difference between these two quantities represents the net work W done by the gas during the cycle, which can be expressed using the first law of thermodynamics as work done equals the heat absorbed minus the heat rejected. This work corresponds to the area enclosed by the process curves on the PV diagram. In essence, the Carnot cycle demonstrates how heat energy can be converted into mechanical work. Significance of the Carnot cycle. The Carnot cycle operates as an ideal heat engine. It sets the theoretical upper limit for efficiency that any real engine, whether it's a car engine or a jet turbine, can achieve. Although no practical engine can be perfectly Carnot efficient due to unavoidable losses like friction and heat leakage, this cycle provides the standard by which all real engines are measured. In real-world applications, the Brayton cycle describes the behavior of gas turbine engines, while the Otto cycle explains how internal combustion engines function. These real cycles are based on the same thermodynamic principles illustrated by the Carnot cycle, but they are adapted to account for the limitations and requirements of practical engineering systems. Real-life example of the Carnot cycle. A good real-world analogy for the Carnot cycle can be found in the operation of refrigerator or heat pump. In these systems, the working fluid, typically a refrigerant, undergoes a sequence of expansions and compressions that closely resemble the processes in the Carnot cycle. When the refrigerant expands, it absorbs heat from the inside of the refrigerator, acting like the cold reservoir. When it is compressed, it releases that absorbed heat to the environment, the hot reservoir. Although no refrigerator operates exactly as a Carnot engine, the efficiency of all real refrigerators is measured against the Carnot efficiency. The closer a refrigerator operates to this ideal, the less electrical energy it needs to transfer a given amount of heat. Similarly, in power plants, engineers use the concept of the Carnot cycle to estimate the maximum possible efficiency of converting heat, often from burning fuel or nuclear reactions, into mechanical or electrical energy. Thus, the Carnot cycle isn't just a theoretical idea. It's a fundamental benchmark that guides the design and evaluation of all real thermal machines, from the refrigerator in your kitchen to the turbines that generate electricity for entire cities. Introduction to aircraft propulsion and thermodynamics. To move an airplane through the air, thrust is generated by some kind of propulsion system. Beginning with the Wright brothers' first flight, many airplanes have used internal combustion engines to turn propellers and produce thrust. Today, most general aviation or private airplanes are powered by internal combustion engines, similar to the engines found in automobiles. Understanding these engines requires considering both the mechanical operation of the machine and the thermodynamic processes that enable the machine to produce useful work. The Otto thermodynamic cycle. The Otto cycle is the idealized thermodynamic cycle used in all four-stroke internal combustion engines. On a pressure-volume PV diagram, the cycle is represented as a closed loop with 6 key stages corresponding to the physical motion of the piston and the opening and closing of valves in the engine. Stage 1 to Stage 2 intake stroke. The cycle begins at Stage 1, where the piston is at the top of the cylinder and the gas pressure is near atmospheric. During the intake stroke, the piston moves downward while the intake valve opens. A fuel-air mixture is drawn into the cylinder, causing the gas volume to increase while the pressure remains approximately constant. Stage 2 to Stage 3 compression stroke. After the intake valve closes, the piston moves upward, compressing the fuel-air mixture. During this stage, the volume decreases, and both the pressure and temperature of the gas rise in preparation for combustion. Stage 3 to Stage 4 combustion at constant volume. At Stage 3, the spark plug ignites the compressed mixture. The combustion occurs at nearly constant volume, sharply increasing the pressure and temperature inside the cylinder. Stage 4 to Stage 5 power stroke, expansion. The high-pressure gas expands, pushing the piston downward. The volume increases, and the gas does work on the piston while the pressure gradually decreases. This stage completes the main part of the power stroke. Stage 5 to Stage 6 exhaust stroke part 1. At Stage 5, the exhaust valve opens. The piston moves upward, forcing the combustion products out of the cylinder. The pressure remains roughly constant while the gas volume decreases. Stage 6 to Stage 1 exhaust stroke part 2. The piston completes its upward movement, expelling the remaining exhaust gases. The cylinder returns to its original state, ready for the next intake stroke, completing the cycle. The network produced by the engine is represented by the area enclosed by the cycle on the PV diagram. In an ideal Otto cycle, there are no heat losses during compression and power strokes, no friction losses, and instantaneous combustion occurs at constant volume. In reality, engines experience losses due to friction, heat transfer, and non-instantaneous combustion, reducing the actual work output. These effects are accounted for using efficiency factors, so the real PV diagram is similar in shape but slightly smaller in area than the ideal diagram. Reciprocating piston engine operation. The real-life examples of Otto cycle are reciprocating piston engines. The reciprocating piston engine operates by converting the thermodynamic processes of the Otto cycle into mechanical motion. The up and down movement of the piston is synchronized with the opening and closing of the intake and exhaust valves using a camshaft. This synchronization allows the sequential entry of the fuel-air mixture, compression and combustion, and the exit of exhaust gases. The operation of a four-stroke engine can be summarized as follows. 1. Intake stroke. The piston moves downward and the intake valve opens. A carburetor or fuel injection system draws the fuel-air mixture into the cylinder. 2. Compression stroke. Both intake and exhaust valves are closed. The piston moves upward, compressing the mixture to a point suitable for combustion. 3. Power stroke. The spark plug ignites the compressed mixture. Expanding gases force the piston downward, driving the crankshaft. 4. Exhaust stroke. The exhaust valve opens and the piston moves upward, expelling the combustion products. The cylinder is now ready for the next intake stroke. Let's have a look at the animation of the reciprocating piston engine. As we can see from animation, we have four strokes we talked about before. Intake stroke, compression stroke, power stroke, and exhaust stroke. Intake, compression, power, and exhaust. Very simple and easy to understand. Take a few seconds and look at the animation by yourself to fully understand all strokes and the working principle of an engine. Repeat each stroke as you see on animation by yourself to remember them easily. A piston engine may also operate on the diesel cycle. In diesel engines, the high compression raises the temperature enough to ignite the fuel without a spark plug. Diesel engines typically offer higher thermal efficiency, lower specific fuel consumption, and in many countries, diesel fuel is less expensive than gasoline. The Brayton cycle. Now we will talk about the Brayton thermodynamic cycle, which is used in all gas turbine engines. The figures show a temperature entropy, TS diagram, and pressure volume, PV diagram of the Brayton cycle. Also on this page, we show an animation of the temperature variation through the engine and the pressure variation through the engine. Using the turbine engine station numbering system, we begin with free stream conditions at station 0. During cruising flight, the inlet slows the airstream as it enters the compressor phase at station 2. As the flow slows, some of the kinetic energy associated with the aircraft's velocity is converted into static pressure, compressing the air. Ideally, this compression is isentropic, meaning it occurs without any change in entropy, and the static temperature of the air increases as shown on the TS plot. The compressor then does work on the air, increasing both its pressure and temperature from station 2 to station 3, which is the compressor exit. In the ideal case, this isentropic compression appears as a vertical line on the TS diagram. In reality, some inefficiencies cause entropy to increase slightly, so the process line leans to the right. From station 3 to station 4, the hot air enters the combustion chamber or burner, where fuel is added and burned at nearly constant pressure. The temperature rises significantly during this process, depending on the fuel type and fuel-air ratio. The high-temperature, high-pressure gas then passes through the power turbine from station 4 to station 5. Work is extracted by the turbine to drive the compressor. Since the turbine and compressor are on the same shaft, the work produced by the turbine ideally equals the work required by the compressor. The temperature drops as energy is converted to mechanical work. Finally, the gas exits through the nozzle from station 5 to station 8, where it expands isentropically to match the free stream pressure. At the nozzle exit, the flow conditions return to free stream, completing the cycle. The area under the curve on the TS diagram is proportional to the useful work and thrust generated by the engine. The Brayton cycle analysis is essential for predicting the thermodynamic performance of gas turbine engines, including thrust, efficiency, and power output. Okay guys, now let's have a little quiz. The quiz consists of 6 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. On a TS diagram, what does the area under the curve of a process represent? The correct answer is the heat transferred during the process. Question 2. In a Carnot cycle, which 2 processes are adiabatic? The correct answer is expansion and compression. Question 3. During constant pressure combustion in a gas turbine Brayton cycle, what happens to the temperature and entropy of the gas? The correct answer is temperature increases, entropy increases. Question 4. In the Brayton cycle, what type of process occurs in the combustion chamber? The correct answer is constant pressure heat addition. Question 5. Which statement is true about the Otto cycle? The correct answer is heat is added at constant volume. Question 6. Which cycle typically has a higher efficiency at high comp ratios for the same working fluid? The correct answer is Otto cycle. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, aerodynamics and structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about gas turbine thermodynamics, from inlet to nozzle. See you in the next video. Bye.